Hi, everybody. My name is Kumar, and I'm accompanied with Ravi from Marvell. So today we will talk about the technologies which are being developed in Ultra Ethernet Consortium. There are a bunch of technologies which are being standardized. There are many of them, and we are working on doing the SAI specification for them. So today we will talk about three of them, CSIG, LLR, CBFC. The way we have structured the talk, we have very short time. We will give you a brief overview of the feature. This is like just a teaser. This will make you, at a very high level, understand what the feature is, or maybe it will not make you understand, right? Yeah. We will talk about the SAI spec enhancements. Again, they're abstractions. We will not go in detail. It's going to be extremely high level. And then finally, we will go through the call to action. So that's the way we have structured. And it's really a power-packed 3 topics. I hope that you get something out of it. So first topic is CSIG that I'm going to cover. LLR and CBFC, Ravi, you're going to cover.
Sure.
So with that, so if people have not yet heard about CSIG, then I would say you have not attended the AI track sessions. CSIG has been talked over again and again. The reason it is that it's such a lightweight telemetry protocol for congestion control, and it's defined in such a manner where, like the earlier technologies like the P4 INT, IOM, and for that matter, IFA, they were very heavyweight on the implementation. So it's very lightweight, and the way it works is there's a packet, endpoint inserts the CSIG tag. It could be 4-byte, 8-byte. Packet traverses across the network. At each hop, it performs something called as a compare and update. And if you see, the packet header has a field called a signal type. Signal type is the kind of signal that packet is carrying. And each hop will do a compare and update. And finally, packet reaches to the endpoint. When it reaches to the endpoint either consumes it if it's doing receiver-based congestion control, or if it's sender-based congestion control, then it reflects it back. So there is a binding of the CSIG tag with the transport. So somebody will say that, actually you are working on a transport, why you are treating it as a layer 2 tag. So this is actually a layer 2 tag in the layering, but it sort of looks like MPLS. It's not layer 2, not layer 3. It sits somewhere in the middle, but the binding of the tag is with the transport. Okay? So the way structure is defined is there are signal type, that's one field, and signal value is actually the computed value, right? SAI specification. So how we have, I have not given the full details, on the CSIG. This is just a high level. Mainly, tag carries the signals. Each signal has an associated math component to it, min, max, sum, etc. And then we have a compare and update. There is also a concept where at some point the CSIG tag needs to be deleted. So the way we have structured in the SAI specification, if you know that there is an object called as TAM. TAM stands for telemetry and monitoring object. And TAM object we defined, I think, almost maybe 5 years, 6 years back, long time back. We define it very comprehensive, where anything to do with telemetry or INT technology, it's a very well-defined infrastructure. It took us a long time to come to an agreement on that. So CSIG will sit in the TAM infrastructure. There is an object called as TAM INT object. That INT object has multiple attributes. First thing you want to know, if the packet is coming in, how do you know that this packet is a CSIG packet? So there is something called as packet identification. So that attribute is enhanced to say that there is a CSIG ETH type as the identifier. Then after that, what are you enabling in the packet to do the signal processing, which is your type of signal. So that's being identified. ACL objects are identified mainly for match conditions, right? Current ACL actions are comprehensive in the sense that they give all the ability to do any kind of INT action we want on CSIG. We don't need any enhancements. Match has been identified to match either on the TPID of the packet, signal type. There is a D-bit, which is associated with the trim. We talked about in the morning, the trim function. It has a binding with the trim. Those are the match conditions which have been identified. The capability query, you need to know the device. Does it support 4-byte tag, 8-byte tag for a given tag, what kind of signals, etc. That capability query is the one which helps you to do that. So that's the way we have structured the object enhancement. Very busy slide. I'm not going to go over it. This is just a set of attributes which have been worked on. And it gives you an idea what all attributes are added. And they're mainly saying that this signal gets enabled, etc. This is the ACL and the INT presence. As I said, the indication of the packet, whether it's a CSIC packet, is defined by an attribute. It's called as INT presence. That has been extended, and the ACL match conditions have been extended. So this is what we have in CSIG, pretty much. I'm going to give the baton to Ravi. Ravi?
Thank you, Jay. Okay. To connect with what we have seen in the earlier talks, the summary what we've been seeing is distributed training applications that run on the backend networks are very sensitive to packet losses. And when a packet is lost, hundreds of GPUs are stalled waiting for end-to-end retransmissions to recover these packets. UEC has defined a couple of features at the link layer to reduce the need for end-to-end retransmissions, namely link layer retry and credit-based flow control. Let's start with link layer retry. Link layer retry is a mechanism where packets lost due to frame corruption can be recovered without needing end-to-end retransmissions. The need for this is as the likelihood of a packet getting corrupted increases as the speed of the links increase. And LLR helps in local recovery of these corrupted packets. The way this works is the sender, when it transmits frames, it encodes a sequence number in the preamble of the frame. And it also stores these frames in a replay buffer. The receiver periodically acknowledges all the frames it has successfully received. On the receipt of this acknowledgement, the sender frees up the frames from its replay buffer. Now when a frame gets corrupted, the receiver detects the corruption, say either by looking at a missing sequence number or by looking at getting uncorrectable FEC errors. And in this case, the receiver sends back a LR negative acknowledgement, and on receipt of a NAC, the sender replaces the buffers from its replay buffer, thereby avoiding the need for end-to-end retransmissions. Now let's come to the main thing, how we have modeled this in the SAI specification. First, we have introduced a new object called the LLR profile. This object models the LLR configuration required. Example, the sizes of the replay buffer, the timers associated with the replay buffer, and init and flush actions of the replay. Next, we have enhanced the existing SAI port object to have the attributes to control turning on, turning off LLR, get the current status of the LLR operation, attach the newly introduced LLR profile object to a port, and lastly, fetch the statistics related to LLR from the port. Important point is LLR does not need any modifications to the forwarding behavior defined by the existing SAI spec. Again, there are a lot of attributes. We'll quickly skim through the attributes. A couple of attributes on the new LLR profile to size the replay buffer. Then the timeouts required for the LLR operation. And the frame actions when the port begins LLR operation and port enters into a failure case. And lastly, attributes to space or tune the period between two successive acknowledgements. Similarly, we have port attributes to turn on LLR, to attach LLR profile, read the statistics. And then there are two types of statistics, one for the LLR RX side, the other for LLR TX side. They allow you to get the various types of control order sets that have been transmitted, received, various types of frame checksum based errors detected, number of replays happened, and then lastly, the different types of sequence errors that have been detected using the sequence numbers. Next, we look at credit-based flow control. While LLR recovers packets that have been lost due to frame corruption, CBFC prevents packet losses due to buffer overflows. Here, it's an alternative to PFC, and unlike PFC. In CBFC, the sender is aware of the receiver's buffer utilization and ensures that frames are transmitted only when the receiver has sufficient buffer space. So the way this works is a concept called virtual channel is being defined. A virtual channel represents a subset of a port's traffic that has unique buffering requirements, unique dedicated and shared buffer. Port's traffic is mapped to a virtual channel using existing packet fields like QoS, packet QoS fields like DSAP, .1p, etc. A port can have up to 32 virtual channels, and the way this works is during initialization, typically via LLDP, the receiver informs the sender about the amount of buffer, typically in terms of credits, to the sender. So sender knows the amount of buffer available for a given virtual channel. And then the sender keeps track of all the credits used when it transmits frames. And whenever these frames are successfully received by the receiver and sent to the higher layers, the receiver frees up these frames and periodically updates the sender using credits freed messages. And this mechanism allows such that the sender now understands how much is the buffer available and ensures that no buffer overflows happen at the receiver side. Now let's look at how we have modeled it in the SAI spec, right? First, we have introduced the new, whatever we talked about, the virtual channel object. The virtual channel object represents, it has attributes to turn on, turn off lossless operation. It has statistics associated to get the virtual channel statistics. And then we have introduced new cost map types, which allows us to derive the virtual channel from a given packet QoS field, to derive the virtual channel from the traffic channel or from the queue. And then we have introduced two new objects called the credit pool and the credit profile. This allows various types of buffer management to be done for a given virtual channel. Then we have introduced attributes in the existing SAI port object. These attributes help in detecting for LLDP negotiation, understanding what's the packet overhead, what is the native credit size, all these things are done using the port object. Lastly, we have enhanced a couple of attributes in the queue object. It's an existing queue object. We added attributes to allow enqueue, disable enqueue temporarily. This is to help set up the lossless operation on a given virtual channel. So this is the idea of what's done at the SAI for CBFC. Then we'll quickly go through the different attributes. Just I'll skim through it. This is the virtual channel object that we talked about. Then the new credit profile and credit pool objects to manage the credits given for a given virtual channel. And then statistics related to the virtual channel about number of credits used, credits freed, credits consumed, etc. Next, this is the attributes that we introduced to the existing SAI port object. Things for LLDP negotiation to understand the native credit size, packet overhead, etc. And to configure the credit management mode, total credits or per VC mode. And then attributes to tune the time between CBFC messages. Attributes to bind the cost maps to help you derive the VC for a given packet. And then lastly, additional new statistics added on the port to get the number of different types of CBFC messages that are being transmitted and the credits used. And then the new cost map types we talked about earlier, which allows us to map derive a virtual channel for a given packet, either from the packet QoS fields or from the traffic class or from the virtual channel or from the queue. Lastly, the two new attributes are the queue to enable DQ or post DQ when you want to set up the lossless operation. So the two new attributes, the existing queue object. That's all about CBFC, what we had to do. And lastly, if you're from the UEC, if you're a member of the UEC, please join in the UEC SAI haddock that's chaired by Jai, where all the specs, these features and all the future UEC features will be defined and modeled and then taken to OCP SAI. And those who want to take a sneak preview of whatever Jay presented and what I talked about, you can look at the links to have a sneak preview of how it has been modeled so far.
Yeah, if I may add, Ravi, as well, the SAI specs for UE 1.0, they're out. If you just Google UEC spec they will show up. LLR and CBFC are already released, so you should be able to go and get a good idea what those details are. The CSIG, we have contributed to OCP. It's a 0.50 version. It's a little old. There are some changes which are happening, but it's a good place to start. It's a good place to start to understand or comment. And if you, again, just go in the OCP networking GitHub, do a Google, it will show up there. So those places are a good place to get an understanding, to contribute. You can come to UEC if you're a member. Otherwise, SAI community is always there.
Wait for the SAI,
Yeah. And that's it for us today. Yeah.
Thanks. Questions? Yeah.
Thank you.
Thank you. Yeah, please go ahead for questions.
Hey, Jay, great presentation, both of you. Thank you. Can you please comment on pros and cons of having one common model like TAM to cover all the different telemetry features versus having lightweight, dedicated SAI object for something like CSIG? The reason I'm asking that CSIG itself, by design, was meant to be this simple and lightweight. So what are the pros and cons of including it in the big TAM model versus having dedicated objects for it?
That's a very good question, and that question actually takes us back in time when we were defining the TAM infrastructure. So anytime you look at any telemetry technology, there are components which are common, okay? For example, every telemetry needs some way for identification. That's common. Actions are very similar. Either you do delete, you do init, right? You do a strip and forward, things like that, or you term. They are very common. The concept of sending the data to a collector is very common. The need for defining the collector, addressing, transport, et cetera, is very common. So when we were we realized that the overlap is so huge that if we take each telemetry technology and start putting independently, there will be a repetition of the attributes. And in SAI, we work very hard to have a very optimal set of attributes. Otherwise, the configuration becomes very, very huge. So having said that, what we did, we gave the flexibility of, instead of creating a one giant container and then try to work on that, if, let's say, there is need for only INT, then there is only TAM INT object. You don't have to create any other object, right? If you have an event framework, then there is an event object. You don't have to create anything. But then there are sub-objects which are common to them, right? So that's the way we make it. And if you see the workflow, it's actually very concise. Even the addition on the SAI specs are very concise. We don't change. So good question. It looks kind of scary because TAM itself is a pretty big infrastructure. But if you look at the implementation in that, it's very, very short.
Just to add on it, right? Before this TAM 2.0 was done, J8 did it. Before that, if you look at what was there in SAI, there are a lot of different ways to do TAM and a lot of confusion. Histograms had a different way to do. There was just too many things in the SAI. And now after TAM 2.0 has come, there have been many features that have been added, mirror on drop, etc. And there what we see is most of the framework is already there. With minor enhancements just like this, right? We can get new features added. And a lot of telemetry features are evolving. And we have not done any major changes to the TAM framework. High-speed telemetry, all this can be done with minor enhancements to the TAM 2.0. So I think it's good to keep one framework and keep adding the knobs. I think that's the way it's been working.
Most of those examples that you mentioned, they're like switch.
I request do a follow-up discussion if you have follow-up questions. Thank you.
Yeah, sure. Thank you.
So this one's on crate-based flow control. Is this overlap with PFC in some ways, or do they solve the same problem in different ways?
They solve the same problem in different ways. The spec allows both of them to coexist, but they solve the same problem in different ways. And CBFC can allow up to 32 lossless classes, whereas PFC is 8, right? It can allow up to 32.
Okay. I mean, so is it likely that you use one, you don't use the other?
Typically, but the spec allows both of them to coexist as well.
Okay. Thanks.
Thank you.
So, just for my understanding, I don't know, standing too close. So, just for my understanding, all the standard is for how to configure and everything. Do you have a standard also for how to get the data, the reports? Or this is like per vendor?
Let me take that away. So in SAI, we have a method to configure. And if you want to get the configured state, what we call as operational state, SAI API is defined to get the information as well. And besides that, you have either the debug state or the counters, and SAI API defined to get that information. Was that the question?
Something like that, but the CSEG information is like per vendor, you get this data from hardware, which is like different formats, right? Or you can it's standardized?
No, it is
counters?
standardized. The format is, that's the whole point of standardization, right? So it's a 4-byte tag, for example. The fields within the tag are clearly defined. The signals are clearly defined what the bit value means in that, right? Not only that, we have gone one step ahead and say the quantization algorithm must be this, because if one hop takes the quantization, which is, let's say, running average, right, versus other one which takes a time interval average, then there will be variation. Then you cannot perform compare and update. They are two different values. So there is a very, it's a very prescriptive method. So there is a consistency in implementation. So you better look at the spec before implementing it in the hardware. Thank you.
Thank you.
Maybe one quick last question. Has it already been discussed with the SAI community?
CSIC? Or any of them? No, not yet. We are in the process of bringing it. So UEC follows certain methods. We have to comply with that. Once the internal review is complete, then we bring it. And our internal review have reached what we call as a version 0.50. Post 5.0, then we are able to bring it here. So that's why we are talking.
So we're already there? So we are about to discuss it with the SAI community now?
We will start working on that. We'll open the PRs, etc.
Awesome.
So that's why we are presenting it here.
Excellent.
So we get the feedback.
Thank you.
All right. Thank you all. Thank you so much.
The last question, yeah.
Hi, thanks for the presentation. Are any of these features implemented by vendors in the existing ASICs, or is it in the pipeline for any of the ASICs?
I can speak for Broadcom. I will let Ravi speak for Marvell. All of these features are present in Tomahawk Ultra. They are present in Thor Ultra. They are present in Tomahawk 6, which is out. Yes.
Yeah, I think I'm from the engineering background. I'll have to work with the NDA, so I'm not sure.
So yeah, I mean, this is public
this is more
information.
from a UC, right? This is more from the UC perspective.
Yeah,
Not from
you can talk offline about
Thank
this.
you.
Yeah. Thank you. Thanks a lot, Jay.
All right, thank you.
Thank you.